Alright, so we're going to jump to a new topic now. We're going to look at introduction to complex numbers. So because it's a new topic, there's not heaps of prior knowledge, but there are some things that would be good to know to help you with this content. Introduction to vectors might seem like an odd one. You might be wondering what that has to do with complex numbers. That will actually be helpful for this, because what we'll see is that we can actually treat some complex numbers like vectors in space, and knowing how to add and subtract vectors will actually be very useful for this. Another thing that might be useful is a video I've made on what numbers exist. So up to this stage, we've been looking at real numbers, and then beneath that you have things like rational numbers and natural numbers and all that sort of stuff. So I'll put a link to that video, it might be helpful to sort of see where this new kind of number sits in the sort of broader picture of things. And there's a fair bit of coordinate geometry stuff that's going to be relevant for this as well, so I can put some links for that as well. So the key concepts we'll cover in this video though are basically the set of complex numbers. We'll look at the real and imaginary parts to complex numbers. We're going to look at operations on complex numbers, so addition, subtraction and multiplication, but division will come in another video. We're going to look at what's called Argand diagrams, and then we'll look at geometric interpretations of operations on complex numbers, and that's kind of where the vector knowledge will be useful. So let's jump into it and have a think about what a complex number is. So a complex number is made up of two parts. You've got what's called a real part and an imaginary part. So if we just think about this idea of an imaginary unit, so mathematicians introduce the imaginary unit I with the property that I squared equals -1. So we can now have a solution to the equation x squared equals -1. Basically, this is going to give us x equals plus or minus I. And so essentially, just sort of following this logic here, I must be the square root of -1. Okay, so once we've known up to this point that you can't really take the square root of a negative number, but now we're just going to say, okay, we're going to call the square root of -1 the imaginary unit. So if you were to take the square root of -4 now, well, the same rules of surds apply here. So you take the square root of 4 times -1, which is the square root of 4 times the square root of -1. Square root of 4 is 2. Square root of -1 is now I, so this is 2I. Okay, and then with that information, we can sort of define the set of what's called complex numbers. Okay, so a complex number is made up of two parts, as we mentioned. It's made up of a real part, a real number, and an imaginary number. And we usually use the letter Z. So Z is a complex number that's made up of a real part, A, and an imaginary part, BI. We note here that A and B are real numbers themselves. Okay, so for example, our imaginary number could be something like 2, which is a real number, plus 3 multiplied by I, where the 3I part is the imaginary part. Okay, and so we can say that the set of all complex numbers is given by this capital C, and it's the set of all numbers A plus BI, where A and B are real numbers. Okay, so you can see how that creates a well-defined set that we call the complex numbers. Okay, if A is 0, then Z equals BI is an imaginary number. Okay, so if this A part goes to 0, then we've just got an imaginary number, a purely imaginary number. If B goes to 0, B times the imaginary unit. If B is 0, then 0 multiplied by the imaginary unit is still 0. So then we just get a real number. So sort of our normal rules of algebra apply there. And so, yeah, we get for Z equals A plus BI, we define the real part of Z is equal to A. So this is sort of a function, capital RE of Z, just outputs the real component of the complex number, and the imaginary, applying this IM of Z, just outputs the imaginary component of the complex number. But it outputs only the coefficient, right? It just outputs the value of B, the coefficient of the imaginary unit. Okay, and then so we say R of Z and the imaginary component of Z are real valued functions. So yeah, the real component, the real component of a complex number is a real number, and the imaginary component of a complex number is also a real number. Okay, so just over here, you'll see we've got this interesting table to explain. basically, we're just going to look at the powers now, and it'll make more sense as we go through. But if we start to think, all right, we take I to the power of 1, well, anything to the power of 1 is just itself. So we get, if we do I to the power of 1, if I set n to be 1, if it lets me, there we go. All right, so we can see that I to the power of 1 is just itself, so that's just I. Okay, we know from previously that anything to the power of 0 is 1, is the real number 1. So I to the power of 0, the imaginary unit to the power of 0, is just the real number 1 with 0 imaginary component. So you can essentially ignore this because this part doesn't exist. Okay, and then we can cycle through them. Okay, so I to the power of 1 is, as we said, I to the power of 2. Okay, we're taking the square root of -1 squared. If you square something that's already been taken the square root of, you just get that thing back that's underneath the square root. So you get -1. So I squared is -1, but obviously we defined that there. So potentially over-explaining that. Anyway, I cubed, let's think. That's going to give us -I, because if we take I squared, which is -1, and multiply by I, -1 multiplied by I is just -I. Okay, and then we'll go to 4, and then it becomes +1, because we're taking I squared multiplied by I squared, which is just -1 times -1, which is +1, and there's no imaginary component. And then you'll notice we actually just cycle through it. It goes I, -1, -I, 1, and then we start again. I, -1, -I, 1, and so on. So we end up with this. I to the power of 5 is I to the power of 6 is -1, I to the power of 7 is -I to the power of 8 is 1, I to the power of 9 is +I to the power of 10 is -1. And then you just go through those cycles in sort of multiples of 4. So that is what a complex number is, but if that was a bit confusing, we'll talk more about it in a moment, so do not stress. Let's talk about hopefully a straightforward idea, which is what's called the equality of complex numbers. So if we do have two complex numbers that are equal, that means that their real and imaginary parts must be equal. So if we've got some complex numbers that are equivalent, so a plus bi equals c plus di, this implies that a must equal c and b must equal d if those numbers are equivalent, right? Sort of like equating coefficients, if you've done that before. So just sort of simply here doing a quick example, if we were to solve 3x plus 2 plus 4yi equals 8 plus 10i for x and y, well, we just need to equate the coefficients. We can see that the real part of the complex number is 3x plus 2, and we know that that has to equal the real part of the other complex number. So we get 3x plus 2 equals 8. Solving that, we get x equals 2. Similarly, 4y, the imaginary component of the first complex number, must equal 10, which is the imaginary component of the second complex number. So 4y equals 10. Solving that, we get y equals 5 on 2. So that's how we can exploit the fact that if two complex numbers are equal, then we can find those values of a and b. Okay, let's look at some operations on complex numbers. So let's first look at addition. Okay, so if we're adding one complex number, which we'll call z1, and some other complex number z2, we just simply add the real components. So we're going to get a plus c, and then we're going to get b plus d, I. So essentially you just add, excuse me, the real components and add the imaginary components. Subtraction, we do the same thing. So it's going to be a minus c plus b minus d, I. Okay, the zero of complex numbers is defined as 0. There's no real part and there's no imaginary part. So that's a 0 complex number. We can also say, we'll talk about what's called the additive inverse. If we're to take some complex number and negate it, then that's the same thing as taking the negative component of a minus the negative component of the imaginary part. So it becomes negative a minus bi. Okay, interestingly, these are all properties you have come across in algebra. We can say for complex numbers that they're commutative. So that means z1 plus z2 equals z2 plus z1. Doesn't matter which order you add numbers. 2 plus 3 is the same as 3 plus 2. It's the same with complex numbers. can also say that it's associative. So z plus z1 plus z2 added together plus z3 is the same as z1 plus z2 plus z3 added together. Okay, additive identity, basically if you add 0 to the complex number, it stays the same. And if you add the negative version of the complex number to itself, then you'll get 0. Okay, and also we can do what's called multiplication by a scalar. So it's basically exploiting the distributive property here. So if you've got some complex number, a plus bi, and then you multiply by k, you multiply the real component by k, and you multiply the imaginary component by k. And this is where k is obviously a real number scalar. That's what we mean by a scalar. You're just sort of scaling it up. Okay, so for example, if z equals 3 minus 6i, then 3z, okay, we're multiplying the complex number by 3, so we multiply the real component by 3. 3 times 3 is 9, minus 6 times 3 is negative 18, so you get 3z equals 9 minus 18i. And so you can see here, this is, it is distributive. K multiplied by z1 plus z2 is equal to k multiplied by z1 plus k multiplied by z2. So it is distributive. This symbol here means for all k. For any k, that is an element of real numbers. And we've got a little picture here that's supposed to be two complex numbers doing operations. Not sure if that came across. All right, let's talk now about what's called Argand diagrams. So this is a really great way to visualize complex numbers. So an Argand diagram represents complex numbers geometrically. Okay, so now rather than think of your Cartesian plane as having sort of real numbers on the x-axis and y-axis, now we've got real numbers only on the x-axis, but we've got imaginary numbers on the y-axis. So this is the real axis and this is the imaginary axis. Okay, so the complex number a plus bi can be plotted as 2 points. So a comma b in Cartesian form. So for example, I think it'll make sense if I show you these. The point negative 2, 1, I think you would agree in Cartesian form is over here. But in complex number land, this corresponds to, all right, the real component is negative 2 and the imaginary component is positive 1. So that sort of corresponds to this spot here. Similarly, this one over here, 3 plus I, we've got a real component of 3 and an imaginary component of 1. So it's 3 plus I. And lastly down here, real component of 2, imaginary component of negative 3i. So it's sort of pointing down here. And so that's how we represent complex numbers on what's called an Argand diagram. Okay. And you can start to see how it's getting a bit geometric, which I think is useful. So let's talk about that a little bit more in terms of our operations on complex numbers. So we'll say that this is the geometric representation of the basic operations on complex numbers. So if we're to take addition, we know from before that z1 plus z2 corresponds to adding the real components and adding the imaginary components. So let's just look at that for a moment. Let's imagine we've got these two vectors, same as before, negative 2 plus I and then 3 plus I. We want to add them together. Now, from the introduction to vectors video, we should be aware that if we need to add vectors, we need to take the vector and we need to put the tail of one vector on the tip of the other. So let me show you what that looks like. It's going to look like this. We're going to take that vector and we're going to add it to the tip of the other vector, and then we connect them like that. So if we were to add these two vectors together, we would get a vector pointing with this size and this size and direction here. Okay, and then so that is our addition of those two vectors. I encourage you to pause the video and think about what is the value of this, but hopefully you can see that it has a real component of 1 and an imaginary component of 2. So if we just display that, the real component is 1, 1 plus 2i. So this point in space here is the complex number 1 plus 2i, and it's the addition of negative 2 plus I and 3 plus I. Okay, so hopefully you found that interesting. Okay, the next thing we can talk about is subtraction. Subtraction just goes the other way, right? Subtraction is addition, but you're doing negative vector addition. So I'll leave that as an exercise for you to think about. Just take one vector and you reverse it and then add them together. Okay, the other thing we can talk about though is scalar multiplication. So let's look at this red vector now, 2 minus 3i. We can scale that up and down by some scalar. Okay, so this slider here just shows some scalar. We can scale that up and down. If this slider went negative, then this arrow would point in the negative direction, but I just haven't got it set to do that. But you get the idea. We can scale that complex number up or down by any number we like, just like we spoke about before with the letter K. Okay, so we end up with something like that. All right, let's keep trucking. Now we get, so we've spoken about addition and subtraction. We've spoken about scalar multiplication. What we want to talk about now is multiplying two complex numbers together. So again, we've got complex numbers Z1 and Z2 defined as the same as before. What we want to do now is we're going to multiply them together. So what we're going to do is we're just going to apply the distributive property, but and see what happens essentially. So expanding this, just expanding it like two binomials, I think you would agree that you would get something like this. Simplifying by collecting like terms, you'll get this: AC plus ADI plus BCI plus BDI squared. But we know that the imaginary unit squared is -1. So we substitute that in. And so this last term becomes negative BD. And then we sort of group the real components and the imaginary components. We can see these middle two have imaginary units in them. So they're going to sort of be grouped together, and these first and last one don't. So they're the real components. So we can see that when we multiply Z1 by Z2, we get AC minus BD plus AD plus BC multiplied by I. And so that is our product of two complex numbers. Okay, and it can be a bit confusing with all the different letters. So let's look at an example. Remember, A, B, C, and D are all real numbers. So let's imagine that our first complex number is 2 plus 3i, and our second complex number is 1 plus 4i. Okay, compute the multiplication of them. 2 times 1 plus 2 times 4i plus 3 times I, 3i times 1 rather, plus 3i times 4i. So you get 2 plus 8i plus 3i plus 12i squared. I squared equals -1, so this becomes -12. 2 minus 12, group the real parts, is -10. 8i plus 3i is 11i. So we can say that when you multiply these two complex numbers together, you get -10 plus 11i. Okay, hopefully that's making some sense. Now let's just look at a bit of a geometric interpretation of that exact same example. So again, the same working out here, nothing new here. But what we're going to do is we're just going to think about what it looks like in space. So down here, we've just got some sliders for A, B, C, and D. We said we're going to say that A is the real component of Z1. Well, the real component of Z1 is 2. So let's set that to be 2. And you can see that it's going to generate a vector that's pointing at the point 2 there, because there's no imaginary component yet. But we can see that the imaginary component is 3. So let's set the imaginary component of Z1 to be equal to 3. And so that's there, right? Okay, at the moment, Z2 is all set to 0, but we're going to change that. And you're going to notice that another vector is going to be generated, and that vector represents the multiplication of Z1 and Z2. And just using the formula that we spoke about, that's going to be represented down here. Okay? And then this is the output. So hopefully you'll see what I mean. So the real component of Z2 is 1, so let's put that to 1. And the imaginary component of Z2 is 4. Okay, so 4 is all the way up here. So if we set that to 4, you'll notice it's sort of computing the result all the way along. But this is the one we're interested in. Oops. Set that to 4. And we can see that it's -10 plus 11i is the product or the multiplication of Z1 and Z2. And you'll notice, if we just play around a little bit, and I'm going to oversimplify this, but you can see that it has a rotationary, I don't know if that's a word, has a rotation effect, right? So as we change these values, we can see that the resultant vector sort of is rotating depending on what those values obviously are, right? So there's a rotation effect and there's a magnifying effect in our Argand diagram when we sort of multiply complex numbers together. One thing I'll just point out, because this is very important and I haven't included it in this video, is that when you multiply by the imaginary unit on your Argand diagram, it has the effect of rotating by 90 degrees. Now, I haven't shown that here explicitly, but just take note of the fact that, for example, if you were to have the real number 2, and then you were to multiply by the imaginary unit, where you'd have 2 multiplied by I, and then you'd be up here, right? You'd be on the imaginary axis at 2i. So you can see how multiplying by I has the effect of rotating by 90 degrees. So that'll be useful for a whole bunch of other things that you'll be learning about soon. But just wanted to point out this example here, and maybe I'll just put it back for good measure. Real component of z2 is 1, imaginary component of z2 is 4. This one is 2 and 3. Anyway, that's just that specific example, but hopefully that's making some sense. Give us a thumbs up if you found this at all useful, and get ready for a whole bunch of new complex number videos as we go along. So good luck with everything, and I'll talk to you soon.